Hello everyone, this is Satyajit Pattnaik and welcome back to my channel. In case you are new to this channel, please subscribe the channel and hit the bell icon to get notified on my future videos and sessions. Today we have with us, hello everyone, hello. Today we have with us Shivani. Shivani is a machine learning researcher focused mainly on novel state of art models in deep learning and machine learning. She has formerly also published novel research approach in ensemble model learning. Apart from that, she's also a part of our data science community where she helps other fellow members and data science enthusiasts. So I recently started working on a deep learning playlist as I talked about in the very last class in the CNN's program. I shall be publishing the same on my channel very soon. So thought of going for a live session on ANN and Keras-Tuner. So initially, I shall be walking you through the concepts of ANN and then I will hand over the session to Shivani so that she can help you understand about Keras-Tuner. Similarly, I also had conducted a session on CNN few weeks back, probably 2 to 3 weeks back, and we had got a positive response. That was the main reason why I came up with this ANN topic. So let's get quickly started on this. In case you have any questions in the middle of the session, you can post it as a comment or in the live chat, and I'll try to get back to you with the answers. If your questions are somehow missed, you can definitely reach out to me or Shivani directly. Links to our LinkedIn profile will also be, I think it's already shared in the description of this video. Okay, so let's get started. So today's topic, as I already told, it's going to be on ANN. So before understanding about ANN, we shall also be understanding about the basics of neural network. However, I have already covered the basics of neural network, the basics of activation functions, how NN works and learns, gradient descent, stochastic gradient descent in one of my previous videos in CNN. But still, I will try to cover from basics so that you understand the basics and then we will move ahead with the ANN part. Okay, so this is the agenda. This is the agenda of my playlist which I shall be publishing in couple of days. But today's session we will almost cover everything apart from CNN. Okay, so we'll try to understand what is deep learning. We'll have ANN intuition. We'll understand what are activation functions, how neural network works and learns, gradient descent and stochastic gradient descent, and we'll also try to build a ANN model and then we'll try to fine tune it using Keras-Tuner. Okay, now before going ahead with the ANN part, we'll try to understand why deep learning. Now let's just give 2 minutes time so that if because I got some pings, people are joining in. Just give 2 minutes and then we will resume from this particular area itself. Excuse me. Everybody is able to see my. Okay, I haven't shared my screen. That's my bad. Okay, so let's get started, guys. So agenda I just talked about. We will understand what is the basic understanding on deep learning, what is ANN and intuition, activation functions, how neural network works and learns, stochastic gradient descent and GD, and we'll also understand what is Keras, TensorFlow, PyTorch, Theano, and again we'll try to build and evaluate a ANN model, and then we will see how Keras tuner can be used to fine tune a model. Okay. So godfather of deep learning, Geoffrey Hinton is called as the godfather of deep learning. He had actually torched the term of deep learning long back, and deep learning basically works with the principles of how human brain works. Okay, now human brain also has neurons. Similarly, deep learning also works in that concept. This particular picture was taken from one of the websites. The image courtesy is already provided, but you can see the difference between machine learning and deep learning. The basic prerequisite of deep learning is going to be you should only use deep learning techniques, deep learning models only when your machine learning models are failing or they are not capable enough to build. Then only it is recommended to go for deep learning, because deep learning, the training time increases, the computational the it is computationally expensive, and it is also the memory also required is more in deep learning. Okay, and of course training time, right? Now you can see the first image is all about how a machine learning flow works. You have an input, then we do some feature scaling techniques, we do some feature extraction techniques, feature engineering, and then we build our classification model, and then we get the output. Okay, so feature scaling, feature extraction, feature selection, the entire feature engineering steps is basically done manually by us, by the developers, by the engineers, by the data scientists, right? But coming on to the deep learning part, you can see that deep learning, the entire process of feature engineering and the model building part is done within the network itself. So there is an input, and then we have the hidden layers, and then we get the output. So most of our feature engineering tasks are actually done internally by the neural network's hidden layers. But there are some ways how to monitor, how to use them wisely, but most of the things are being managed internally by the neural networks. Okay, now neural network intuition, we'll try to understand what is neuron and what are the basic activation functions, how neural network works and learns. All these topics we will cover. As you can see in this image, neuron is a basic building block. Okay, and you can see there are some parameters within a neural network that transforms. So weights are basically the parameters within a neural networks that transforms input data into a within a neural network hidden layer. Let me draw a small neural network so that you can understand. Now in machine learning, I know that I have an input, and then I do some feature scaling techniques, feature engineering techniques. Then I create my model, do some hyperparameter optimization here, and then I get my output, right? In deep learning, what happens is your inputs are passed through an input layer. Let's say I build my input layer something like this. Let me build it and then I will explain. Okay, now obviously all the arrows are connected with each other. You can draw it by yourself. It will be okay, something like this, something like this. Okay, now basically this is basically called as your input layer in in your neural network. This is called as your hidden layers, and this is called as your output layer. Now why one neuron in your output layer? Could be a reason that it's a binary classification problem, so we have one output, so it will predict whether one or zero, or cats or dogs, or something and something, right? So binary classifications. Now we have four neurons in my input layer. What does that mean? That means I have four independent variables: x1, x2, x3, and x4. I have defined five neurons each in my hidden layers, and there are two hidden layers in this particular model, in this particular network. Okay, this is basically a neural network. Now, what happens in neural network is we have a concept of weights. Let me explain you using a small example for a better understanding. Let's say I have x1, I have x2, dot dot dot, I have xn. And here I'm drawing just one neuron to make it for a better understanding. And then I have my output, or you can call it as y or y hat, whatever it is, predicted values. Now, each this is also a neuron, and this is also a neuron. Each neuron is connected with each other, and there is a weight assigned to it. Now what is a weight? Weight is a parameter within a neural network that transforms input data within the neural network's hidden layers. Okay, neural. So the basic understanding is that weights is nothing but it represents the strength of the connection between units. Now, if this is W1, this is W2, and this is Wn. If W1 is greater than W2, that means this connection is more stronger than this connection. That means this X1 is a more important feature than X2 for this neuron. Okay. Similarly, you can make it look more complicated. You can create multiple neurons in your hidden layers, and you can imagine, because each neuron in your hidden layer will be connected to your input layers, right? So let's say three inputs, and I have five hidden layers. So this hidden layer will be connected with this, will be connected with this, will be connected with this. Not necessarily all these weights will be similar. Okay, these weights will differ, and based on like how powerful the network is, how powerful the connection is, the weights are created. Now, how the weights are initialized, there is a configuration in the neural networks how the weights are initialized. Okay, understood. So what happens is here, so the formula is basically I equals to 0 to n wi(xi). So weights into multiplied with inputs. This particular thing is also associated with something like this. Now, what is this? Wi(xi). What is this? This is nothing but your activation function. Activation function. Okay. I'll have a detailed video on activation function, but however, I will explain you in brief so that you don't, I mean, you understand properly before implementing your ANN model. Activation functions are nothing but it actually tells that whether you should activate a neuron or not. As simple as that. Okay. Basically, it calculates a weighted sum of its inputs, adds bias, and then decides whether it should be fired or not. Okay. And this basically, let's say the formula becomes y equals to summation of weights into inputs plus bias. Okay. Now there are multiple activation functions. We will study about each one of them in brief. Uh, these are actually used in your hidden layers. So the first activation function is step function. What is a step function? Let's consider a threshold based activation function that activates the value that activates based on a threshold value. Okay, this image is a example of a step function. You can see the x axis we have here 0 and 1, and the y value is 1 when the x value is more than 0, right? So only when x is greater than 0, your output, that means your y value is 1. That means your neurons are activated only when x is greater than 0. When x is less than 0, your neurons are not activated. These type of functions are very basic functions. It is only meant for theoretical knowledge. Most of the times we don't use step function in your practical applications. Okay, but if you want, you can use and see how the model behaves. Okay, so one of the example is binary classification problem, but there is a drawback. As I told, it is one of the basic functions. The drawback of step function is that what happens when more than one neuron is activated in that case? Multiple neurons will have one value. So multiple neurons will have a value of 1, and predicting an output will be a problem, mostly in a multi-class classification problem. So what happens is, let's say I have three input values, three input neurons, four neurons in my hidden layer, two hidden layers, and it's a multiple classification problem. Okay, so we have three neurons in my output layer. In case this value is also 1, this value is also 1, and this value is 0, how will you predict whether it is class A or whether it is class B? So this is a drawback of your step function. Okay, so step function, if you want to use in your practical applications, you can use it in your binary classification problems. Next one is linear function. As you can see, linear function is a straight line function. we already know that linear function is nothing but y equals to mx plus c, right? Where m is the slope and c is the intercept, right? So here you can see the line goes through x-axis. That means the formula here will be y equals to mx, correct? And the derivative of y will be x. Sorry, the derivative of y will be m, right? So here the function is basically a straight line function where activation is proportional to input. Your input increases, your y value increases. Your input decreases, your y value decreases. Directly proportional to your input. Okay. Now a equals to mx, derivative of which will be m, which is a constant value, which means gradient has gradient has no relationship with x. It is a constant gradient and descent is going to be a constant descent. Now what is gradient? Anybody has any questions? No. I was just checking the chat box. So what is gradient? Let's try to understand what is gradient. Gradient, sorry about the handwriting. Gradient is nothing but change in y divided by change in x. It is otherwise called as delta y by delta x. So one example is, let's say I will draw a line and let's say this is the line. So this point is 2, 3 and let's say this point is 8, 6. Okay. So what will be this coordinate? In the x-axis will be 8 and the y-axis will be 3, right? So here the delta y, that means the change in y is how much? It is 3 units. 6 minus 3, right? In the x-axis, the delta x is nothing but 8 minus 2, which is 6 units. So here the gradient is delta y by delta x, that means 3 by 6. That means gradient is 0.5. Okay. So the gradient increases when the line becomes more steeper. That means if the line is something like this, so here the gradient will be more than 1 because delta y is greater than x, greater than delta x, right? So here your gradient will be greater than 1. If your line is less steeper, something like this, or let's say something like this, here delta y is very less, very closer to 0. Delta x is very high. That means here your gradient is almost equivalent to 0. Okay. So the linear functions are also having a demerit. They have their own drawbacks. Okay, the drawback is that in each and every hidden layer, if you use linear functions, in first hidden layer also linear, second also linear, third also linear, combination of a linear function is always linear, right? So we cannot use linear functions in multiple connected layers. That is one drawback. But yeah, you can use linear functions in one of the hidden layers or two of the hidden layers. Now the next activation function is sigmoid function. Sigmoid function, as you can see the graph, it is non-linear in nature. Okay, I will just redraw it. So this is basically a sigmoid function, and this is how the sigmoid function looks like. Sorry, very bad. Okay, something like this. This is 0.5 and obviously this is 1 and this is 0. That means the range is always between 0 to 1. Sigmoid function formula is nothing but 1 by 1 plus e to the power of minus x. Okay. Now the derivative of a sigmoid function is, if you do dA of dx, you will have to do a derivative of 1 by 1 plus e to the power of minus x. Okay. Now the value of it you can calculate by yourself. You can take help of mathisfun.com or any of the online portals where you can easily get the derivatives of a function. Okay. But as an exercise, as a exercise, what you can do is try to put multiple x values and try to get the a value, and then you can automatically plot your diagram and your graph will be something like this. Similarly, what you can do is you can take the derivative of this function, and then with multiple x values, you can also try to find the value of your a or the derivative of a, and then plot your graph. So basically it looks like this, the derivative of a sigmoid function. Properly I will explain in in my playlists. So the range always ranges from 0 to 0.25. Okay. Now the advantage of sigmoid function is that it is non-linear in nature, and you can see some of the characteristics of sigmoid function is in this range. In this range, your gradient is more than zero point 0.5 at least, right? The gradient is more, but in the edges, you can see the gradient is almost zero. Here, if you calculate the gradient, because it is delta y by delta x, right? So delta y is very low. So gradient is almost equivalent to zero. That means your neurons are not learning in the edges. Okay, that is the demerit of it. So, as I told, towards your ends in this particular graph, toward your end, y values tend to respond very less changes to x. Okay, which means gradient is very small, which otherwise means that network refuses to learn further or is drastically slow. And this is where your network is very active. Okay, our next type of activation function is tan-h function. Tan-h function is also very similar to sigmoid function. Its range is between -1 to 1, and the formula is a equals to uh, 2 by 1 plus e to the power of minus 2x minus 1. Okay, and again what you can do is for different x values, -1, x equals 2, x equals to -2, you can find yourself what is the a value and then plot it. Okay, so this is how the graph will look like. Okay, so this is 0, this is -1, and this is 1. Okay, this is how the graph looks like. It is very similar to a sigmoid function. It is also known as scaled sigmoid function. Now, what is the relationship between tan h and the sigmoid function? Tan h is nothing but 2 times of sigmoid of 2x minus 1. This is the relationship. Okay, characteristics again very similar to sigmoid function, non-linear in nature, and the range is -1 to 1, right? But again, they have their own drawbacks. Sigmoid function has its own drawback. If I start talking about it, it might take more than 1 hour, 2 hour to cover. Okay. So there is a problem in sigmoid and tanh functions. That was the reason why Relu was introduced. Our next topic is Relu activation function, rectifier unit. Okay. Now what is Relu? Relu is nothing but a equals to max of 0 to x. That is the formula of Relu. So when x is greater than 0, then a equals to x. When x is less than 0, a equals to 0. If we draw this, this is how it will look like. This is x and this is my a. When x is less than 0, that means a equals to 0. For x is less than 0, a is equals to 0. For x greater than 0, a equals to x. Okay. Okay, this is how your Relu function looks like. The range of Relu is always between 0 to infinity. It is again non-linear in nature, and combinations of a non-linear function is always a non-linear function, right? So we can stack layers because of its non-linear nature. Now imagine a very big neural network with a lot of neurons. Now using a sigmoid or a tanh function will cause almost all neurons to activate in an analog way. That means almost all activations will be processed to describe the output of a network. In other words, activations are dense. This is costly, right? So ideally, we want few neurons in a network to activate and thereby making the activation sparse. So ReLU basically gives us this benefit. But again, as I told, that machine learning and deep learning is all about hit and trial. Nothing is perfect. So ReLU has its own drawbacks as well. Now the drawback of ReLU is that you can see that when x is less than 0, sorry, yeah, x is less than 0, then the neurons are not learning anything, right? It is also called as neurons are dying. They are not activated, right? So this particular problem in ReLU is called as dying ReLU problem. Might be asked oftenly in the interviews, what is dying ReLU problem? This is nothing but neurons goes into a state where they don't respond. Okay, that also means gradient is 0. That means the delta y is 0. It's not equivalent, it's not almost 0, it is 0. Okay, now how to get rid of dying ReLU problem? There are certain ways to get rid of dying ReLU problem. Now obviously the problem itself causes several neurons to die and they does not respond, making a substantial part of the network passive, right? This is the area, this is the area where the network is passive, and this is the area where the network is active, right? Now to get rid of this, what happens is when x is less than 0, what we can do is we can assign a very small value. Let's say y equals to 0.01x. Now if we draw the diagram, how it will look like? Obviously when x is greater than 0, it will be y equals to x. When x is less than 0, for x equals to minus 1, y equals to minus zero point 0.1. So it will be something like this. Okay, that means the gradient is not 0, but the gradient is almost 0, but it is not 0. Okay, so to make the gradient non-zero, we do these kind of changes. This is also called as leaky ReLU. Okay, now coming on to the advantages of ReLU. Now ReLU was again, the history of ReLU is ReLU was introduced in 2000 because before that, what happened is, I will just tell you a small story. So researchers who were using neural networks long back in 1980s and 1990s, they were not making a very dense neural network. Okay, so the neural networks which they were using is was having like one or two hidden layers, not more than that. So Sigmoid was serving the purpose. Now, today's day, if we use Sigmoid or Tanich function in each and every hidden layer, what happens is there is a problem called as vanishing gradient problem. Okay, in brief, I will tell you what happens is, let's say I have three hidden layers, and in each hidden layer, I'm using a Sigmoid function. Before that, let's say my W1 is 5. Okay, my first weight is 5, and I'm using a sigmoid function. Now, as I told you, sigmoid function's derivative always ranges from 0 to 0.25. Okay, now considering the best possible value, the best possible value is 0.25. Second layer 0.25, third layer 0.25. Now, what happens is the new weight in neural network, there is also a concept of back propagation. We do a forward pass and then do a backward propagation. Okay, so once we backward propagate, then the weights are updated. So after each and every run of, like when you train your model, you define your epochs. That means how many times you want to train your model. So for each and every processing time, processing of your neural network, for each and every run, what happens is you do a forward pass, you initialize the weights, again based on your output you back propagate and update the weights. That's how the neural network learns from its mistakes. Let's say the new weight will be w1 dash equals to 5 into 0.25 into 0.25 into 0.25. Now if you do this, this will be a very small value. It will be somewhere around 0.01 or something like that, which means the initial weight and the next weight, the new weight, you can see the fluctuation is too much. So this is also one of the problems called as vanishing gradient problem. Okay, let's not go into depth, but yeah, to overcome this issue, when we started using multiple hidden layers, we started seeing this vanishing gradient problem. That was the reason why Relu was introduced in 2000. Okay, now again, if you ask me a question that which activation function to use, which activation function to prefer, again that will come by your experience. Slowly and steadily you will understand that. Okay, uh, that's it about the activation functions. I covered almost everything. Okay, back propagation and forward pass. So what is this? I just explained it in brief. What happens is randomly we initialize the model with weights. Less weights initially. Input your first observation. That means first row of your data set in input layer. Forward propagate from left to right. So neurons are activated in a way that input of each neuron activation is limited by weights. So propagation is happening till the output layer to get the y hat. Y hat is nothing but the predicted y value. Sorry, the predicted y value. Now, okay, I will just explain using a diagram. So let me define a small neural network. Let's say three input neurons, hidden layers, and let's say one output. Let me draw it. Okay, something like this. So what happens is I have 1,000 records. Okay, let's say I feed in my first record. Weights are initialized W1, W2, okay, n number of weights. Okay, I cannot write each one of them. So weights are initialized and we forward propagate. Okay, for this record, we already know that whether it is a class A or class B, right? Now, what we do is we compare that value. So let's say this record was actually class A, okay, and we have predicted it as zero point 0.5. Okay, so it has to be more than zero point 0.5. It is not zero point 0.9 or zero point 0.8. Okay, it is zero point 0.5. So what happens is we calculate the cost function. That means how the predictions are actually behaving. Is the network learnt enough or they haven't learnt? Okay, and then what happens is this is basically called as forward pass. Then we backward propagate, and then what we do is we rechange the weights. Okay, so new weights are assigned, and again we forward propagate, then backward propagate, and this is where the neural networks learn from its mistake, and it runs till it gives you a very perfect output. Okay, so the number of times it runs is basically user defined. Okay, you will understand what should be the optimum value of that once you start working on a neural network. This is the basic concept of forward pass and backward pass. Comparing y hat to y, calculate the cost function. Back propagation from right to left, the error is back propagated. Update the weights according to how they are responsible for the error. The learning rate decides how much we update the weights. Okay, and we have to repeat this till we finalize a model. Frameworks and libraries I will not discuss in this session because it will be too much to explain. But just a brief overview that TensorFlow was basically created to replace Theano. It was created by Google and it's recommended framework for deep learning. The pros, obviously Theano is a very like it's a very old framework not being used recently. Recently TensorFlow and PyTorch are the mostly used frameworks. Okay, now what is the difference between TensorFlow and PyTorch? Quickly we will see the differences. TensorFlow was basically created by Google. PyTorch was created by Facebook and it is new to the market. It was launched in 2000, late 2017. Okay, I think TensorFlow was launched way back in 2014. Not pretty sure about the year, but yeah, PyTorch is very new. TensorFlow is a to-go tool for the researchers. It is a preferred tool. Now, the reason being it has been in the market from a long time as compared to PyTorch. PyTorch is new. So, researchers are still using TensorFlow. Okay. But yeah, there are a lot of people who are also using PyTorch. Debugging wise, There is a concept of TFDBG which is used, which allows to evaluate TensorFlow expression at runtime and browse all tensors and operation in scope. When it comes to PyTorch, we have PDB and IPDB, PyCharm debugger, or old trusty print statements by which we can debug the codes. TensorFlow, for the visualization point of view, we have TensorBoard. In PyTorch, we have Wisdom. But coming on to the rating wise, I would rate TensorBoard more than Wisdom. Okay, TensorBoard is a very matured visualization tool, and it is good as well. Like as compared to PyTorch, it is better. Deployment, TensorFlow has its own TensorFlow serving, and PyTorch we have to write our own RESTful APIs or Flask APIs on top of the model to make it deployable. Data parallelism, it's a manual process to run in parallel over GPUs in case of TensorFlow. In case of PyTorch, we have a torch.nn.data parallel to wrap any model, and it will almost be magical to parallelize over patch dimension. So for data parallelism, PyTorch can be a clear winner. Okay, developer friendly. TensorFlow is less developer friendly as compared to PyTorch because of multiple reasons. Okay, now Keras versus TensorFlow. I will just try to skip it. I will help you out with this PPT. You can go through this PPT later on. And the main topic is going to be building an ANN network. Okay, so let's try to build an ANN network and see how the model behaves. Now, before going to the building of an ANN network from the code point of view, what I will do is I will try to create a basic machine learning model using one of the algorithms, maybe decision tree or a random forest, and then we will see how the model behaves on that particular use case, particular use case, and then we will try to implement ANN, and we'll see how the model behaves, whether we have a better accuracy or we our classical machine learning models are behaving better. So let me write down the code for you all. Actually, I have already written the code, but yeah, let me write it down in front of you so that we can understand each and every line properly. So again, I will just import my pandas library. Matplotlib.pyplot as plt. Yeah. Oh shit. Let me just restart it. So I have the fine tuning part block here, but yeah, I don't have the basic code. So we'll have to execute line by line. So this is how the importing of the libraries work. Importing libraries. So I will talk about a very similar use case which I uh, showed in one of the live projects a couple of weeks back. So it is a churn prediction model. So I will define my data set pd dot read csv churn modeling dot csv. Okay, this is how the dataset looks like. Customer ID, surname, a lot of attributes are there. We are not concerned about the ADA and all those things. So I will quickly, what I will do is I will simply call encoding categorical variable. Let me write it down. Label encoder. I think I must be having a code. Okay. So I already have a code. So let's just run this program. Okay, I have just restarted the console. So I already have the code actually. I have read the dataset from the churn modeling CSV. X equals to, I have taken all the values just except, you can see the dataset. This is how the dataset looks like. We have row number, customer ID, surname, a lot of things. In X, okay, X is it's an ND array, so it's not visible. What I have done is I have just skipped the row number, customer ID, and surname because these are basically not required for the model building part. So I have taken the values from credit score till the estimated salary. and for y block we have taken the exited one. Okay, here I'm performing an encoding, so just ignore that part. I'll call my test and training split. I'm using 80% as training data and 20% as test data. Then I am calling my scaling technique, feature scaling. Okay, now feature scaling, most of you might already be knowing that in order to process your data in the models, feature scaling plays a vital role because we have to scale down the values to a certain range. Now, why feature scaling? Maybe you can just go for a Google search, you will understand. So once feature scaling is done, I'm just calling my decision tree classifier with the default values. I haven't passed any of the parameters here. I'm just randomly calling my decision tree classifier. So classifier is called, then I'm fitting the classifier and I'm calling the predict function on the test data. Here I am calling the confusion matrix. Okay, this is how the confusion matrix output looks like. Okay, 1364, 220. If I calculate the accuracy, it should be 1364 plus 220, 1584. 1584 divided by, okay, 79.2%. So the accuracy is 79.2%. Let's run this same program with a random forest classifier. I'll just change the code to ensemble import random forest classifier. I will just pass n estimators equals to 100. Rest everything remains same. CLF2, I'll just rename it CLF2, CLF2. Okay, that's it. Let's name it CM2, CM2. Okay, let's run it. So here the output is little bit better as compared to the decision trees. 1513 plus 205, 85.9%. Okay, so the accuracy is 85.9%. This is a very generic use case, generic data set. So it is quite obvious that we will get higher accuracy without even doing feature engineering, right? Because we haven't done any kind of feature engineering here. We have just randomly taken the values without performing any EDA. We are just passing the values to the model, still getting a good accuracy, right? So this is all about the classical machine learning part, right? So using decision trees, we got 79.2. Using random forest with a good amount of trees inside that, n estimate is equals to 100, we are able to achieve 85.9% accuracy. Okay, now our next step is to create a ANN network. So here I will show you how I have created the ANN network. I will just explain each and every line with you. So before that, if you have any questions, just let me know. I will just take a 2 minutes pause or a 1 minute pause so that you can ask questions if you have anything. Okay, I can see a lot of questions. Oh. Okay, Irshad, what is the difference between slope and gradient? Okay, sigmoid. I'm sorry, I have missed a lot of questions. Irshad has tried to help. Sigmoid function used in classification problem. Yeah, mostly. Yeah, see, where and when to use your activation function, that comes by experience. Okay, just by explaining you the activation functions, I cannot give you a thumb rule that use this one here and this one here, right? But normally you can use your Relu functions in your hidden layers, and if it is a binary classification problem, only when in your output layer, in your very much output layer, you can use sigmoid function, you can use a step function, or you can use a Relu function as well. Okay. Sigmoid function can also be used in one of the hidden layers or two of the hidden layers, not in every hidden layer. But again, that's a hit and trial which you need to do and see how your model behaves. Is it deteriorating or is it increasing in accuracy? Any other questions? Uh, 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 I think Sivani has answered a lot of questions. In case you have any questions which I am not able to answer because of some reasons, you can ping me on my LinkedIn directly. Okay, so let's try to create a basic ANN model with just three hidden layers without much knowledge on the hyperparameter optimizations. We'll build the basic ANN model and we'll see how it behaves. So here you can see that I have imported the library. So I'm using Keras. Keras is basically a wrapper class, and internally it uses TensorFlow and Theano as its backend. But the default backend it uses is TensorFlow. Okay, so let me run this code. Sequential is nothing but my Keras model classifier. Okay, and dense is used for the defining the layers. Okay, only for ANN network we define our hidden layers as dense layers. For CNN we have separate other layers like conf 2D, conf 3D, pooling, flattening, all those things. And when it comes to LSTMs, they have their own layers, like they have their own LSTM cells, right? So here I'm initializing the ANN. I have called the classifier equals to sequential. Okay, here I'm defining the first input layer. Now you can see first input layer, I have just defined classifier dot add dense units equals to 6, kernel initializer equals to uniform, activation equals to Relu, input dim equals to 10. I will explain one by one. Units equals to 6. What is this? This is nothing but how much units are you defining? How much neurons are you defining in your hidden layer? Now you can ask me what is the thumb rule for this. The thumb rule which I use is units equals to, you always start with, it should be the input dimensions plus your output dimensions divided by 2, the average of that. Now your input dimensions, you can see x is nothing but 10 dimensions, right? It is a 10 dimensional array. So 10, your output is it's a binary classification model. So your output is going to be 1. So 10 plus 1 by 2, it's 5.5. You can use 5 or you can use 6. Kernel initializer is nothing but, uniform is nothing but, like kernel initializer means how your kernels are initialized. Uniform means how your weights are being distributed. It is uniformly distributed or how is it distributed. So we have used uniform. Activation, as you already know, this is the activation function. So we should always start with Relu. And as this is the first layer, how the neural networks will understand that how many input do we have. Do we have 10 inputs? Do we have 20? Do we have 50? So input dim equals to 10. That means our x variable has 10 input values. Okay, so input dim has to be declared only in the first layer. Second layer and the next layers it is not required because neural networks knows that the input dim is 10. Similarly, I have just copy pasted these values and I have created two more hidden layers. So all total I have three hidden layers. Okay, so this is my first layer and they have the second hidden layer and the third hidden layer. Now in the output layer, you can see that dense units equals to 1. Why? Because it is a binary classification problem. We are expecting our output as one output, one neuron in the output layer, right? So this problem is nothing but I have 10 inputs, dot 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 10 inputs, and I have hidden layers. I'm defining three hidden layers and then I have one output here. Okay. After I have defined my output, let me run this. I'm calling the I'm calling the compilation step. I'm doing classifier.compile. Optimizer equals to Adam. I will explain you what is this. What is an optimizer? Optimizer is nothing but it's an algorithm to use optimal weights. Now there are multiple optimizers which can be used. there are Adam optimizer, RMS prop optimizer, and there are many more optimizers. You can just simply go for the go for the Keras documentations. You will find a tons of optimizer. Now, which optimizer is the best? We don't know. We are just calling the basic ANN model. Which one is best? That we will study in the hyperparameter optimization part. Okay. Loss function. This is a binary classification. So I am using a binary cross entropy loss function. Metrics, I'm using accuracy as my metrics. So till, okay, compilation I have already run. So our next step is, once the compilation is done, I will call my fit function. So as this is a small data set, I'm just calling epochs equals to 25. So it will run it for 25 epochs. Okay. Batch size is 10. Batch size 10 means how many records am I running in one batch? 10 records each in one batch, and then your weights will be updated. Okay. Obviously, the optimum value of epochs is not 25. You can run it for 200 or 300 or 500 to gain more accuracy. Okay, we don't have that much time in this particular class, so I'm just running with the basic, you know, just 25 epochs, and see, just with 25 epochs, just with 1 minute of learning, 1 minute of training, we are able to get an accuracy of 83.55%. Okay, so you can print the confusion matrix. This is how the confusion matrix looks like. Accuracy is 83.55. Obviously, random forest is better, but again, as I told you, right, machine learning and deep learning, you just have to do a hit and trial. Then only you can come to a conclusion which model is going to be more effective. So apart from that, I have few more codes. I will just leave this part to you so that you can go through. So okay, I'll just explain this part probably, and I will. Okay, I'll just explain this part. So our next topic is going to be fine tuning of a ANN. Okay, how to fine tune. So there are two major steps in fine tuning an ANN model. One is evaluation of a model, and the next one is improving and fine tuning. So in this particular step, we will be understanding k-fold cross validation. Okay, now what is k-fold cross validation? Most of you might have already used that train underscore test underscore split, right? Now there, we have seen that when we start working on models, what happens is, let's say we are using train test split, and I have 1,000 records. I have divided the data into 800 training data and 200 test data. I have created a model on 800 records, and I am testing on 200 records and getting the y hat value. Okay. So there are chances where most of your information will be in your test data. In this case, what happens is your model is trained on less informations. Okay. It is trained on 800 records, but boundary level informations or more informations are not present. So that is the reason your model is performing well on the training data, but when you are testing on the test data, probably you are getting a very low accuracy, 50% or 60%. Could be because of multiple reasons, overfitting and underfitting. Okay, so k-fold cross validation, what it does is it creates k different types of iterations. Let's say you define k as 10. What happens is, out of 1,000 records, let's say I have like this. First 800 records, it will define as train. Next 200 as test. Second iteration, this is train, this is test, and this is train. So randomly, it what it does is it randomly creates a training and test samples, and then runs your model through multiple iterations. And then let's say you have k value as 10. That means there are 10 different models. Now you will get 10 different accuracies, right? Let's say your 10 different accuracies are 81, 82, 80, 79. 84, and something like this. That means your accuracies are not varying much. It is within the range of 879 to 84. That means your model is performing well. But in case in one of your k-fold value you are getting 85% accuracy, in one you are getting 40%, that means there is some problem with the data, so you have to take care of it. Okay, so k-fold cross validation is also a very important thing. So let's try to run this program. What I have done is I have just imported the libraries. I have created a function. Inside the function, I have simply copy pasted this code from this to this. Okay, from the input layer till the compilation step. I have just copy pasted it. You can see input. This is the input layer. This is the second hidden layer, third hidden layer, and the output layer. Then I'm returning the classifier. Okay. Then what I'm calling is I'm calling my Keras classifier. Build function equals to build classifier. That means I'm calling this function. Batch size is 10 and epochs is 1. Okay, that means I'm running it for one epoch. Because if I run it for 10 epochs, 10 epochs into 10 models, you can imagine the time taken will be more. So I will run it for one epochs, and you can take it as a assignment and you can run it on multiple epochs. Okay, so let me run this code. Obviously it will take a little bit time. So let's go for a 2 minutes break while it runs. Once we come back, we will see the output of this one. In the meanwhile, I can just walk you through the hyperparameter optimization steps as well. So this is your cross validation step. This is your evaluation step, how you're evaluating your model. Once you are done with the evaluation step, parameter optimization. And the variance is, you can see the accuracies. You can see there are 10 different accuracies, right? Because we have defined the CV value. That means my k-fold value is 10. So it has 10 different values. You can see 78, 79, 80, 78, 81, 81. That means the variance is very low. If I just print the variance, you can see the variance is just 1%. Just 1% variance. That means it is a good model. Your evaluation step is successful. But again, as I told, I'm running it on lower epochs. You can use it for, you can run it for 100 or 200 epochs and then you can finalize it. Okay, that's all about the evaluation step. Next is your hyperparameter optimization step. Now this is nothing but I have just you can see the imports. I have used grid search CV, and rest most of the code is very similar to this previous code. Okay, I have created a function. I have called the same, copy pasted, and I'm returning the classifier. So here what I'm doing is I'm calling the classifier, Keras classifier, build function is build classifier. Here I'm defining my parameters. I don't know what is the optimum value of batch size. Optimum value of batch size could be 10, could be 20, could be 50, could be 60. I don't know. I have just randomly populated this as 10. So you can populate more values here, 20, 40, 100, something like this, 512, okay, 256. And epochs. How much epochs? Epochs could be 1, could be 5, could be 10, could be 20, could be 50, could be 100, could be 200, could be 500, could be 1000. And once you run this, you have to run this code. I cannot show you because it will take a hell lot of time. So once you run this code, you will get the best parameters. It will tell you that for batch size 20 and epochs 500, you are getting the best accuracy. Okay. And what is the best accuracy? You can print grid search dot best score underscore. So you will get the best accuracy. Okay. So next step, this step is just to let you understand about the hyperparameters. Okay. Next step, I have written down the code for more parameters, batch size, epochs, loss functions, and optimizers. Again, I will pass this code to you so that you can run this code and practice yourself. So that's it about ANN. We have covered a good amount of topics today. We have also seen how the basic ML model works and how the ANN base model works. Okay. Now what I'll do is I will hand over the code to. I'll hand over the session to Shivani. Shivani, maybe you can get started with your screen sharing.
Okay, am I audible?
Yeah, you're audible, Shivani.
Okay, great. So I'll start my screen share.
Sure. In the meanwhile, if you have any questions, guys, you can just post in the comment box. I will start reading it.
Okay, so just give me a heads up if my screen is visible and I'll start over here.
Yeah, it's visible, Shivani. You can just go to the tab.
Okay, great. So I'll be walking you guys through the notebook of ANN with Keras-Tuner. So in the initial part of the notebook, it's just going to be the same code that Satyajit just explained you. And
Shivani, just yeah, yeah. That's the only thing. Yeah, you can continue. Sorry.
yeah, so yeah, no worries. So I'll be walking you through the code that Satyajit just explained, and I'll also show you the outputs, which we couldn't see formally. Okay, so basically, when we ended Satyajit's session, it was ended mainly on hyperparameter tuning. So generally, in ML, if you need to optimize your models, you need to tweak in a lot of hyperparameters based on what or how many, like, basically how complex your model is supposed to be, or how much of the layers you need to drop. So there's different ways to do that, and you have to manually keep doing that by brute force. And to avoid doing that, there's actually a library called Keras-Tuner. So you could find the documentation for that over here. So Keras-Tuner was mainly released in 2018 or 2017, I guess. It is going to help you. It's actually built upon TensorFlow 2.0, because just make sure that you have the requirements for the, Python 3.7, or any version above 3.6, and TensorFlow 2.0. Now, one of the reasons why you want TensorFlow 2.0 is because it has Keras installed in it, so you don't have to manually install it. If you're working with lower versions of TensorFlow, then you'll have to first install Keras, and then you can install Keras-Tuner from this code. So in Keras-Tuner, basically you can create a lot of hypermodels, and you can search through what kind of parameters you want. So I'll walk you through what is a hypermodel and everything. Um, Before we start, I would want to tell you that this entire session, or not the entire session, at least my part, was based on this blog that I recently wrote a few days ago. Which is, so if you want more details on how to work with Keras-Tuner, or if we have missed out anything, you can just go and check out the Medium blog. It will give you how to build any. So in this blog, I worked with mainly regression with Keras-Tuner. You can use that, or you can understand how to build your own model in Keras-Tuner as well. So starting off, I'm going to first load in the data set, and then we are going to set up the entire data. We're going to run our feature training, feature scaling, and all of those things. And then we have the first model that Satyajit showed us. The confusion matrix for that is over here. And then we use Keras for another model where your output would be something like this. You can see over here if you run it on 25 epochs. And then you go through all of these. So coming back to ANN hyperparameter optimizations, we use grid search over here. Now you have already understood grid search. So if you want to like just go through the outputs, it was like the best score that we got from grid search was 82.78%. I'm going to show you how to do this with Keras-Tuner, like how to optimize the hyperparameters with Keras-Tuner. Now, before we get into hyperparameter optimizations, what exactly is a hyperparameter? It could be anything. So when you create a model, you essentially have the number of hidden layers, which could be a convolutional layer, which could be a dense layer or a fully corrected layer or any other kind of layers that we have, or flatten or global max pooling or anything like that. So the number of those layers, then the number of input units, or which kind of optimizer you're using, what is the loss function you're using, that is your hyperparameters. So let's start off by installing Keras-Tuner. So you can just copy this code and it'll install everything for you. If you're working outside of Jupyter Notebooks or Google Colab, you could just paste this into your terminal and it'll download Keras-Tuner for you. Before that, before starting with the actual code and before creating the hypermodel, we are going to import some necessary libraries. So I will be importing TensorFlow. And from TensorFlow, I'm also getting Keras, and we are also getting the dense layer to work with. We'll also need time because whatever models we're getting from the Keras-Tuner, we'll have to save it in a directory that we can go back again and check. And from Keras-Tuner, we're going to import these two hyperparameters and random search. So random search is essentially going to help you search for any hyperparameters randomly, and hyperparameters which just give you the hyperparameters. Now going to the hypermodel. Now, what exactly is a hypermodel in Keras? So in Keras-Tuner. So like we knew, this is your model code, right? So when you go here to build classifier, this is your model. Now, if I want to put or if I want to tweak in some hyperparameters separately, if I want to like add in, if I want, let's say that this is going to be my first layer. This is your first layer. And from here, let's say I want for I could say I want this in the range of 4. So let's say I want my second layer to be uh, to to be iterated 4 times over. So if I want this to come out 4 times, then I will be just looping it over, and then I could just basically change this value of 4 anything. It could be n. So this was an intuition to what a hypermodel is. You just specify an HP, any variable over here. I'm going to go with HP, and then you could just uh, like tweak in more values. Let's go into the details below. So coming back here is the same model. I've just replaced the variable classifier with a model so that we avoid any confusions. So when we create a sequential model, which was exactly the way it was in the previous code, so in our build model function, we'll give a variable called HP, which is essentially a hyperparameters. So let's create a sequential model with one dense layer, which is your first layer. And then let's say you want your second layer, you're not sure how many hidden layers should your network have. So I'm going to give it a range from 1 to 4. It could be any number of layers from 1 to 4, the number of hidden layers basically. And then my output layer is going to be having 1 unit with the sigmoid activation. Essentially, it should be um, a label which is 1 or 0, which is, let's say, if we're doing a dog versus cat classifier, then let's say it could be a dog or it could be a cat. Now, when you build a hypermodel, a few things that might be different for you are hp.in, this could be different. And the other thing is, this could be different. So what we do over here is when you look at hp.in, when you look at this function, when you look at this block of code, what we are doing here is we want to set the number of units in the first dense layer. So we're not sure what is the best number of units it should have. So I'm going to leave it to Keras-Tuner to randomly pick any number of input units, and I specify the minimum value from 6 to a maximum value of 12. So what Keras-Tuner will do is when I run this entire block of code, what Keras-Tuner is going to do is it's going to, in the first layer, what it's going to do is it will just pick any random number from 6 to 12, and it has to be an integer because we are calling hp.int, and then it'll create a first layer from that. And in the second block of code over here, we again have hp.int, but here we are going to change the entire number of these hidden layers. So from I in the range 1 to 4, it could be any number of layers from 1 to 4. It could be 3, it could be 2. Again, it has to be integers. And then we are going to create a dense layer, but those dense layers would be having 6 units, and the kernel initializer would be uniform with the activation relu constant. Now, if I want to change that, then again, I'll just, if I'm not sure again what number of units I want, I could just again go with hp.int, and then we go with input units, value, we can set it to 3, and sorry, um, and let's say the max value is 5. So in the second layer, it's in the, so let's say in this block, again, we'll be having this. All right, let's do a thing. Let's make sure that we know which layer is this from. We'll just add I. So we know which layer is it is the input unit from. So in this first part of the code, now, if you're wondering what exactly this is, it's something that you can set on your own to know which parameter is the tuner giving you. Now, this is going to be the same. There are 3 types of initializer in Keras-Tuner, which could be hp.int, hp.float, and hp.choice. So if you want to use for your learning rate, you could either go with hp.choice or hp.float. But if you go with hp.float, then there'll be like lots of them. Let's say if you set a float value from, the minimum value could be just um it could be 0.01, and the maximum value could be 0.1. So there are a number of values between those two values, and that'll just make it very heavy essentially. So we'll just use the choice parameter over here. And also, if you want to change the activation, if you're not sure which activation do you want, so in that case also you can just use hp.choice. And what hp.choice will do is, this will be your learning rate or any string that you want to provide it with, and it'll take any of the parameters that you specified in this list. So let's say if I want to use it for activation, then I could just replace the values with Sigmoid or Relu or any other activation functions that we have. Okay, so now we're going to go ahead and compile our model. So once we compile our model, let's instantiate the tuner with random search. So random search is essentially the it's one of the type of tuners that Keras-Tuner is going to provide you, where you build your hypermodel or hypermodel. Okay, so hypermodel is just the model which has the hyperparameters which will be assigned by Keras-Tuner. So that's your hypermodel. So if we have to build the hypermodel, we'll instantiate it with random search. There are more of those. If you check the documentation, you could get to know about it. Let's say, for example, um, so here, if you see, so there's hyper-ResNet, there's hyper-exception, and there are other types of models that are available. You are free to choose from whichever you like. We're going to go with random search for now. So when we instantiate the model, we want to save all of the log files into the log directory that we created up here. And we want to test the validation accuracy. So now, because here the metrics is accuracy, I want my tuner to optimize the validation accuracy. So that I'm going to put in the objective. So objective is basically what do you want to optimized. So I could just put validation loss. In that case, it will just make sure that the validation loss is reduced. Now, max trials essentially is how many number of models do you want to build? So how many number of random models rather do you want to build? So I could specify anything that I want. I will just go with 5 models for now. And then executions per trial is essentially how many times do you want to run one model. So if I just specify one over here, and then if I set executions per trial to be 3, so what exactly is going to happen is my one model would be running 3 times. So the same model, if it is running 3 times, okay, so now you might be wondering, okay, why do I want to run the same model 3 times? Generally, it's a good practice to do because if you're training with machine learning, then you don't want your model to be like, okay, this was a random shot, so I just got a good accuracy once, but then I'm not getting it again. So for ensuring like getting the average, you want to run like at least 3 times, or 2 times works fine as well. So I'm going to set this back to 5, and the executions per trial would be 3. Let's save it all, and then okay. So now we're going to search for our hyperparameters, and this is pretty much similar to your model.fit parameter. So we're just going to go with tuner.search, and we are giving the giving the training features and the labels. So here we're going to provide with the xtrain, which is your training features and your training labels, and the validation features along with the validation labels. And then you set your number of epochs that you want to train every model for. So when you run that, um, let's go back to our previous code. All right. So when you train your model, when you train your tuner, it's going to be running through every epoch. I'm not sure why isn't it showing that right now, but it'll show every 5 instances that it trains, and it'll be running exactly like this would be trained for 10 epochs, and then it'll just finish that over, and then it'll run the second model, and it'll also show you like, okay, this was the first time it was done, and the second time it was done. Once all of those 5 are finished, all of those 10 are finished, um, then we can save the tuner, or we could just get the result from the tuner. So if you want the result summary, these were the results that we got from the tuner. So our objective was the validation accuracy, and the direction was we had to maximize the validation accuracy. So if I set this to loss, then the direction would be minimum. Okay, so these are the trial summaries. So these will be sorted based on the highest to the lowest. So your first model is going to be the best, and then your last model is going to be the one that didn't perform so well. Now, if you want to get the best hyperparameters, and there's a lot of other um, like sections available in Tuner that you can use. There's get best model, there's get best hyperparameters. So we're going to just call up the first model from here. So we're just getting so what tuner.get best hypermodel does, get best model does, is it's going to return um, this entire thing to you. And from this, you want the first one because it's the best. So for that, we're going to call it at the 0 index, and then we're going to get the values from there. So input units 11, learning rate 0.02, and number of layers 2. So what you understand from that is input units from the first layer. This has to be 11. This has to be 2. And yeah, your learning rate was 0.02. So from here, the best model you're getting is if you use the learning rate 0.02 and the other hyperparameters. So you can just tweak in manually, and then you can run your own model, or you could just save this model that you got. So just to make things clear, this is actually a TensorFlow model. This is not any other model. You will actually get a TensorFlow model out of this. So I'll just go ahead and print out the summary of this. This is how it's going to look like. And if you want to save the models that you have got, I'll just save all of these that we have over here into the pickle object. So to save them into the pickle object, I am going to save it with, again, now we have the time imported, so we're going to save it as the same, and then we're going to dump it as the tuner of and the pickle object. So you could see that we have two pickle objects over here. Let's just go ahead and remove these two and save the one that we have. Okay, maybe I'll just remove one of these. Okay, let's check what do we get. We can load in this one. Let's load in this pickle object. And if you check, then if you, okay, so this is your temp tuner. The previous one was your tuner variable. So if you load back the tuner from the pickle object, you're still going to get the best model, and it'll again be a TensorFlow model. So you can reuse this, and you can get the best parameters using Keras-Tuner. So that's it from my side. I guess I'll hand back to Satyajit. If you guys have any questions, please go ahead. We'll be more than happy to answer.
Okay, thank you, Shivani. I think obviously it's very. I mean, we have just gone through a 30 minutes session on Keras-Tuner, which is not quite. It will take time for you to understand, guys. So you just take yourself a good amount of break. You can go through the presentation again. You go through the documentation of Keras-Tuner, and definitely will understand, right? So thanks for joining me for this session, Shivani. Keras-Tuner for me was very informative, and I hope the rest of my part was informative too. Hopefully, we can also collaborate for similar sessions in the future as well. And I'll keep this call open for 2 minutes in case anybody has any doubts, or else we will just wind it up.
Yeah, that sounds good.
Okay, I don't see any comments. Okay, anyways, everybody has my LinkedIn profile, and Shivani's LinkedIn profile is also provided in the description below. Without her permission, I have provided her LinkedIn profile. I'll also share her blog link in the description as well, so that you can go through and understand each and every step of how she has implemented the Keras tuner part, because manually performing hyperparameter optimization in a neural network is a headache. So definitely you will have to use Keras-Tuner. It is very helpful. So go through that blog and try to get your basics done and try to implement, like try to practice more and get hands-on experience. Okay. So thank you all for joining the session. I will
Okay,
also share. Yeah. Sorry. Tell me.
sorry to cut you off, but just in addition, if you guys want the link to the notebook as well, we'll add this below in the YouTube description to the video. So you can go ahead and implement that on your own. So basically, the notebook consists of. Okay, can I probably share my screen again for the next 2 minutes?
Sure. You can.
All right. So if you look at the notebook, if you check the notebook out, it has Satyajit's code as well, and it has our email IDs. If you want if you have any doubts, then we'll be more than happy to address them. It has Satyajit's code, and then from here there'll be the implementation of Keras-Tuner, and that'll be all. So we'll provide the link to the same, and yeah, that's it from my side.
Okay, thank you, Shivani.
Yeah.
Yeah, I was planning for that only. So we will share the codes with you all, and in future also we'll come up with a lot of sessions so that we can interact more, because people learn more from live sessions actually, because a lot of YouTube channels are there, they are providing videos with no doubt, but live sessions are always beneficial, right? So that's it from our side, guys. Thank you all for joining the session. I'll also share my Telegram group link in the description or in the pinned comment. So just join our group for future updates. I also have some few sessions lined up on various topics such as time series analysis, RNN, sales analysis dashboard in Power BI, and a lot more concepts or a lot more topics in this particular channel. So please subscribe my channel and keep me motivated to share my videos as much as possible and like the videos. Thank you everyone and good night, and thank you once again, Shivani.
Thank you so much, Satyajit. And yeah, guys, go ahead and subscribe his channel. He's teaching amazing things.
Thank you.
Yeah.
Bye bye.
Okay, thank you. Have a good day.
Yeah, bye bye.
Bye.